Okay, so this is 5.2, law of cosines, or cosine law. So this will be another set of equations that relate the angles and sides of a triangle, just like what the law of sines did, except this one's going to involve cosines. And this one is particularly important because we're going to be using it later on in our class as well. All right, the setup is the same. We have a triangle, alpha, beta, let's say gamma, A, B, C. Let me write down what the law of cosines is first, and then we'll talk about where it comes from, and then we'll use it in the context of chapter 5, which is solving triangles. And then in the future, we'll use it again. All right, so there's 3 law of cosines. So they go like this. C, so the first one is going to involve kind of C as the core, right, or the base. So C squared equals A squared plus B squared. So I wanted to write this one first because the first thing you should think is Pythagorean theorem, right? C squared equals A squared plus B squared is the Pythagorean theorem if you have a right triangle where the hypotenuse is C. But this is not a right triangle. This law of cosine, these laws of cosines are going to work for any triangles. And so you don't expect this to be true because we know this is only true for right triangles. So actually there's a other term, a correction term, 2ab cosine gamma. All right. So that's the first of the 3 laws. So the way to kind of remember this is basically you have the Pythagorean theorem, and then you have a correction term, this second guy. All right, because the Pythagorean theorem is not true for non-right triangles. The correction term involves your 2 sides, A and B. So this A squared, B squared, you've got an A and a B here. All right, and then you have an angle, gamma. That angle is the one that corresponds to C squared, to C, right? It's the angle that's opposite to C. All right. You need a 2 there, and you need a minus sign. Okay, notice, so I'm calling this kind of an extension of the Pythagorean theorem to any old triangle. And you can see that it is in that if we did have a right triangle and C was the hypotenuse, then gamma would be 90 degrees, right? And if gamma is 90 degrees, cosine of 90 degrees is 0. And so this second term, this correction term would be 0. And that's exactly the Pythagorean theorem, all right? So this really is a correction to the Pythagorean theorem for any old triangle, for any random triangle, not just right triangles. Okay, so the other 2, so once you've kind of understood this one, the other 2 are actually exactly the same in spirit. So the other 2 are going to involve A and B. So the second one is, let's say, based on B. So B squared is equal to, so it's always one side is equal to something to do with the other 2 sides. All right, so the other 2 sides are A and C. So A squared plus C squared minus 2AC, so the other 2 sides. And then cosine of your original guy, beta in this case, because we started out with B equals, right? B goes with the beta, right? And then again, this A, C, all involve the other 2 sides outside of B. So you can probably guess the last one. In fact, it might be a good idea to pause the video and then see if you can write down the last one. And if you can, then you've probably gone a long way towards understanding the form of the law of cosines. Okay, A squared equals B squared plus C squared, right? Always kind of the core guy that we're writing equals, it equals something. The other side is the other 2 sides, right? So B and C, so minus 2BC, and then cosine of alpha, because alpha corresponds to the A. All right. So it looks kind of terrible that first of all, there's 3 of them, but all 3 are in a way very, very similar. And also, it's not as terrible in that it's easy to remember the structure of the law of cosines, right? Of how it should look. Okay, so this gives me three equations that relate the angles and the sides. And for us in this section 5.2, we're going to use these equations to solve triangles again. And in particular, we're going to use it to solve the two situations that we weren't able to do with the law of sines. Or at least we actually would be able to do it, but that would be too difficult to do with the law of sines. All right. Okay. Let me first talk about why the law of cosines is true, and then we'll talk about solving triangles. Okay, so let's draw a triangle. Oops. So I'm only going to prove one of these. The other two are in exactly the same spirit because of the symmetries of these three equations. So let's do our usual alpha, beta, gamma, A, B, C. All right. Okay, actually, I'm not going to need gamma. I'm going to be doing the one with the alpha. So I'm going to be showing this one right there. All right. Okay, so what I'm going to do is I'm going to drop the perpendicular because, again, my law of cosines involves a cosine. And because I'm working with triangles, I would like to see some right triangles. Because if I have right triangles, I can relate that cosine alpha to side lengths, right? And so that allows me to kind of deal with the cosine alphas, all right? Okay, so now I have a right triangle. Let's see. I'm going to, because I have this right triangle like this, I actually have kind of two sides. I've split C into two pieces. So I'm actually going to name the pieces. I'm going to name this first piece C1. Oops. I'm going to name this first piece C1. I'm going to name this second piece, well, actually, if the whole thing is C, then the second piece is C minus C1. All right? So C1 is from here. Let me do it like this. C1 is from here to here. And C minus C1 is from here to there. Okay, now let me look at the two right triangles I've created. So I have a right triangle right there. I have a right triangle right there, right? I'm going to use the Pythagorean theorem. So Pythagorean, I guess I should give this vertical height a name. Let me call it y. So Pythagorean theorem on a left triangle, the one that goes from here to there and back, has hypotenuse b. So its Pythagorean theorem says b squared is equal to c1 squared plus y squared. Okay. Second right triangle has hypotenuse a and side lengths y and c minus c1. So a squared is equal to c minus c1 squared plus y squared. Okay. All right. What I'm going to do is I'm going to subtract the two equations. And this makes sense because y is not a natural quantity in my triangle, right? My triangle consists of A, B, C, alpha, beta, and gamma, right? Y is just a length that I made up by dropping the perpendicular. So I would like to get rid of y's out of my work, especially since my law of cosines up here, right, has no y's in it. So I definitely feel like I need to get rid of the y's. And if I subtract these two equations, that gets rid of the y's. So I subtract them, b squared minus a squared is equal to c1 squared minus c minus c1 squared. And the y's cancel. All right, let me simplify the right-hand side. This is c1 squared minus, and in parentheses, c squared minus 2cc1 plus c1 squared. Okay, let me distribute that negative sign in. c1 squared minus c squared plus 2cc1 minus c1 squared. All right, and luckily enough for us, the c1 and the minus c1 cancel out. So we just end up with minus c squared plus 2cc1. All right. Okay. I'm going to, I want to deal with the C1 because C1, again, is not a natural quantity in my triangle, right? It was created by me by dropping this perpendicular. And also it doesn't show up in the law of cosines. So I don't want to see it. How do I get rid of it? Well, C1 is this length down here, right? Alpha is this angle here. We have this right triangle with hypotenuse B there. And so we see that the relationship between those three is cosine alpha equals C1 over B, adjacent over hypotenuse. And so that allows me to convert C1 equals B cos alpha. All right, so this C1 down here, I can rewrite as B cosine alpha. And now these are all the ingredients I need. I've gotten rid of all the terms that I've kind of made up, the y's and the C1s. And now I just have to reorganize. Let's see. I'm going to throw the a to the right-hand side. And I'm going to throw the minus c to the left-hand side and the plus b, cb cos alpha to the left-hand side. So I end up with b squared plus c squared minus 2 cb cos alpha equals a squared, right? And that's actually the law of cosines that I've boxed all the way up here, right? You can compare them. The ordering is different. A squared is on the right-hand side. But on the other side, we have the b squared to c squared. We're subtracting the two sides multiplied together, b times c. In this case, I've written it as cb. We have cosine of the angle that's opposite to the a, right? So that's exactly the law of cosines. All right, and again, just like the law of sines, the trick was, or the technique was, to drop the perpendicular, and dropping the perpendicular allows me to express my trig functions in terms of sides, and that allows me to kind of figure out exactly what identities I need to work with. All right, so maybe a good exercise for you is to figure out one of the other, or both of the other two cosine laws, or law of cosines. And if you're able to, then that probably will go a long way towards, first of all, helping you understand it, and also remembering the law of cosines. Okay, so now let's use it. So we're going to use the law of cosines to solve triangles. In particular, we want to use it to solve the two situations that were hard to handle with the law of sines. But before we do that, let me kind of clear something up. We have three laws of cosines, right? C squared equals a squared plus b squared minus 2ab cos gamma. B squared equals a squared plus c squared minus 2ac cosine of beta. And then a squared equals b squared plus c squared minus 2bc cosine of alpha, right? But we also had the two law of sines, right? We had sine of alpha over a equals sine of beta over b. We had sine of beta over b equals sine of gamma over c. And let me write down the third one, sine of alpha over a equals sine of gamma over c. But remember, that one actually comes directly from the other two, so that one's in a way not independent. And we also have that the alpha plus beta plus gamma is 180 degrees, right? So this is slightly mysterious if you think about kind of the philosophy that we talked about last time, where solving triangles involves kind of filling in where I give you three of the sides or angles, and you have to figure out the other three, and you have to available to you the two law of sines and then the 180 degrees property, right? So that would be having 6 bits of information and 6 unknowns that you have to figure out, right? But now it looks like we have 1, 2, 3, 4, 5, 6 bits of information, 6 equations. So it seems like we have too much, right? If I give you these 6 and then I give you, 3 sides, isn't that 9 bits of information versus, 6 unknowns? Well, it's not, because the reality is that If you pick 3 of these, for example, let me say it like this. If you pick, for example, the 3 law of cosines, right? From them, you can actually get the 2 law of sines and the 180-degree property. Okay, so these 6 are not independent, actually. They actually are dependent upon each other, depending on their combinations. So another of these combinations is if I pick any 2 of these law of cosines, any 2, and then I pick the 180-degree property, then from those 3, I can actually, the other 3 are dependent on those 3, all right? And so on. So these guys are actually not independent. So while it looks like we have too many equations versus unknowns, we actually don't, all right? So another way you can think of it is that, for example, the 3 law of cosines are an alternate way of writing the law of sines plus the 180-degree property. All right. So it's just an alternate point of view, which is very useful because in certain circumstances, this point of view will be easier to deal with. And that's exactly what we're going to see right now. So last time we said, let me do a summary. We had a whole bunch of possibilities for solving triangles where I give you 3 bits of information, right? Three of the sides or angles, and you're supposed to give me the other 3, right? And what we dealt with last time, what we said last time was this one is no good. These 3 go together as law of sines very easily, right? We use law of sines to deal with these 3 super easily. We said these 2 were the same and both were law of sines. And these 2 were kind of a pain because they had potentially 0 solutions or 1 solution or 2 solutions, and you always have to worry about that. Okay, we said the law of sines, using those to deal with the other 2, SSS and SAS, was difficult. And luckily enough for us, law of cosines will deal with these guys super easily. All right, so let's deal with SSS first. So SSS is a situation where I'm giving you 3 sides. A, B, C, alpha, beta, gamma, right? I'm giving you this, this, this. And remember, for the law of sines, these 3 are exactly the pieces of information that make the law of sines not work too well, because every equation you write down will have 2 unknowns. All right, but I think let's look at the law of cosines right up here, right there, right? Notice that this is perfect for the law of cosines, because if I just, let me actually just write one of the law of cosines down. C squared equals A squared plus B squared minus 2AB cosine of gamma, right? Okay, what do we know? Let's circle. We know A, B, and C. Know that, we know that, we know that, we know that, we know that. So there's actually only one thing we don't know here, gamma. So immediately we know we can get gamma, right? We can throw everything else to the left-hand side and then take the arc cosine. All right, so this would be C squared minus A squared minus B squared over minus 2AB is equal to cosine gamma, right? And so gamma, we can take the arc cosine, C minus A squared minus, C squared minus A squared minus B squared over minus 2AB, like that. And we've got gamma. That's it, right? So all we have to do is plug in the numbers, use our calculator, and we're all set. Okay. Remember when we did this with sine, we had to worry about the fact that when we're solving sines, there's infinite number of solutions, right? So technically, what we want is to solve this equation. And there's actually an infinite number of solutions, just like with sine, right? With sine, the problem was that when we got our solution, right, let's say our solution was there was another one right there, right, within 100, that's less than 180 degrees. Okay, but now let's look at cosine. The graph of cosine looks like this, right? between 0 and 180 degrees, right? We only care about 0 to 180 degrees because we're working with physical triangles, and physical triangles can't have negative angles, and physical triangles can't have angles bigger than 180 degrees, right? Because the total sum of the angles has to be 180. Okay, this right here is 90 degrees, right? When we solve this arc cosine, right, what's going to happen is we're going to get an angle, maybe something like this, right? But there is no other solution, right? This is the only thing that's at this height, right? This guy here is the quantity where that's the c squared minus b squared minus c squared minus a squared minus b squared over minus 2ab. But it doesn't touch cosine again between 0 and 180 degrees. So it's actually the only solution, right? Again, the problem with sine was that there were two places between 180 degrees that we could have the sine equal to the quantity that we're looking for, all right? Here, there's only one touching, all right? So law of cosines is very nice in that we get gamma equals arc cosine of this guy, and we don't have to think about another solution because of the structure of cosine, again, versus the structure of sine, all right? Okay, and that's it. That gives us gamma, all right? What about alpha and beta? Same thing, right? If I use a squared equals b squared plus c squared minus 2ac cosine of alpha, you know, the other, the other law of cosine, except this one for alpha, for a, and we circle the terms we know a, we know b, we know c, we know a, we know c, so therefore we can get alpha, right? In the same way, we throw everything else to the other side, we take an arc cosine, and then we're all set, right? And there's only one solution because of the structure of cosine, okay? And then once we have two of them, the third one, 180 degrees minus the other two, right? So finally, at this point, we would have known alpha and gamma. So beta is 180 degrees minus alpha minus gamma, all right? Or if you wanted to make yourself suffer, you could figure out beta independently, right? Because b squared equals a squared plus c squared minus 2ac cosine of beta, right? So again, using this law of cosines, you would know all of these terms. So you could figure out cosine beta that way as well, all right? So regardless, super easy, right? If you know three sides, then you can solve the triangle really, really easily, provided, of course, you can calculate arc cosine. All right. But again, in this section, these sections 5.1, 5.2, we're assuming that you have access to a calculator. All right. Okay, so that very, very easily solves the SSS situation for us, right? And remember, I really, really want to emphasize, if you tried this with law of sines, right? These three guys you know, and now each of these individual equations, whether you look at this one, or you look at this one, or you look at the outer two, will have two unknowns. So it's really hard to deal with. Okay, now for SAS. That's the last one, right? So that's the last situation that once we've dealt with this, we can solve any triangle, right? Provided you give me 3 bits of information. And provided it's not AAA, of course. And of course, with the caveat that you can have situations where there's no solutions, right? That can occur up here with the SSS situation, where just like we saw with the sines, if I end up with somehow arc cosine of something bigger than 1, then there is no solution, right? So then there is no triangle, okay? So that can definitely happen. But you obviously will see that if you try to take the arc cosine of a quantity that's illegal. All right, SAS. So how do we deal with this? Luckily for us, let me draw a picture. So SAS would be, we know A, B, C, alpha, beta, gamma. We know a side. Oh, sorry, this is backwards. We know an angle, and then it's two sides on either side, right? Alpha, beta, gamma, A, B, C. So we know a side, angle, side. So let's say we know this, 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 right? The angles between the two sides. Okay. This one's really straightforward as well, because if we look at the law of cosines regarding the a, right? So a squared equals b squared plus c squared minus 2bc cosine of alpha. Let's look at what we know. We know this, we know this, we know this, we know this, we know that, right? So instantaneously, we have alpha, we have a, right? Because actually, we don't even have to solve anything. All of the right-hand side, we know everything here, okay? And so we have a. And once we have a, we're all set. Because now we're in the situation where we have side, 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 right? So now, oops. Now, so once we have a, it's side, 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 all right? So use law of cosines again to get beta and gamma, all right? That's it, right? And I'm emphasizing to use the law of cosines here as opposed to the law of sines, because as we've seen, the law of cosines in a way is more straightforward. You take the arc cosine and you're done. You don't have to worry about two solutions, right? Which the law of sines is a huge pain. You have to worry about, possibly having two solutions. Okay, so use the law of sines. Using the law of sines is often, at least from our point of view of doing these problems, more straightforward. Okay, so so essentially what happens is SAS becomes SSS, and SSS is, let me put it in quotes, easy, right? I believe what the book does is they want you to use the law of sines, but again, and then what they do is they set it up so that the law of sines only has one solution by looking at a specific side, right? This is where they look at the side that's the longest. But that means an extra level of memorizing stuff. Here, you don't have to memorize. You just recognize SAS becomes SSS. SSS, you know how to do it. Straightforward, no ambiguity. All right, so I like this idea a lot better. Okay, and again, SAS, if you tried it with the law of sines and you circled the terms that you knew, it's obvious that it's hard to deal with, right? And here, even if you write down the wrong law of cosines, you can easily see that if you write down one of the other ones, let me actually do it. So if you write down c squared equals a squared plus b squared minus 2ac cosine of gamma, and we circle the ones we know, right? We know b, we know c, we know alpha, but alpha doesn't even appear here. So this one is going to be hard to work with because you end up with an equation where you don't know c, you don't know a, you don't know gamma, right? So the only one that's natural for this particular problem is the one that we used. All right. So in this way, SAS is fairly straightforward. Okay, let me do a couple numerical examples very quickly because again, this is quite straightforward, and then we're pretty much done. Except we'll talk about the SSA in this context of the law of cosines to see something interesting. All right, so let's do an SSS example. So solve triangle where A equals 5, B equals 6, C equals 8. All right. So in other words, we want alpha, beta, gamma. All right. Okay, and again, we just directly quote the law of sines. So let's do the C one first. 8 squared equals the other twos, right? 5 squared plus 6 squared minus 2 times the other two, 5 times 6 times cosine of gamma, right? So this tells me immediately that, let me actually write out the number. 64 equals 25 plus 36 minus 60 cosine gamma, right? And so this tells me if I subtract, let me add these two first. So this is going to be 1161, 71. 61, sorry, minus 60 cosine gamma. And so 64 minus 61, which is equal to minus 60 cosine gamma. And so we end up with with 3 over minus 60 equals cosine gamma. And so cosine gamma is equal to minus 1 over 20, right? And so gamma is equal to arc cosine minus 1 over 20. And the minus 1 over 20 might look a little weird to you, but it's not a problem because here's 180 degrees. It just means that the angle you're going to end up with is going to be bigger than 90 degrees, like maybe something like that. All right. Actually 1 over 20, so it's probably going to be very close to right there, close to 90 degrees, all right, but bigger than 90 degrees. All right. So you plug that into a calculator and you're all set, right? If you want any of the other sides, do exactly the same thing. So in particular, let's say I'm only going to do one more of these. And again, here, if you want a number, you just plug it into a calculator. Let me do another one. Beta, let's say we want beta, right? So we have A is 5. So beta would be, we want to write down 6 squared, so B, right? So we're using the law of cosines that's based on B. So 6 squared equals 5 squared plus 8 squared minus 2 times 5 times 8 times cosine of beta, all right? And then we just calculate again. So these are really, you're really happy to see these problems, these law of cosine problems. So this is going to be whatever, right? Let's subtract this to the other side. 64 minus 80 cos beta. Let me subtract on the other side again. 11 minus 64, whatever that is minus 80 cos beta, right? So cos beta is equal to 64 minus 11 over 80, which is 53 over 80. So beta equals arc cosine 53 over 80. Okay. Plug that into a calculator and you're all set, right? 53 over 80 is positive. So this one's going to end up being a angle that's less than 90 degrees, of course, because our first one was already bigger than 90 degrees. You can't have a second one that's bigger than 90 degrees as well. And then what is alpha? Well, now you just take 180 degrees minus beta minus gamma. All right, that would be the most straightforward, most quickest way to do it, right? You don't have to do another arc cosine. Okay, and again, if I'm doing these and I end up with having to calculate arc cosine of 15, then there's no solution. All right, and that can definitely happen. You can definitely set up the numbers, A equals something, B equals something, C equals something, so that you end up having to take arc cosine of a quantity that where arc cosine is not legal. So for example, if I made this C into an 80, almost certainly that would happen. All right, so you'll see that on the homework. So just be careful, of course. You don't want to be taking arc cosines of illegal quantities. So in that situation, no solution. Okay, and for an SAS example, numerical example, let's say A equals 5, B equals 6, gamma equals 37 degrees, right? So alpha A, beta B, gamma C, we would know A, B, and gamma, all right? Sorry, this is a 6 here. It looks like a 0. Okay, again, we know gamma, A and B, so therefore, if I write down this one, law of cosines, it's going to be very straightforward because this is equal to 5 squared plus 6 squared minus 2 times 5 times 6 times cosine of 37 degrees, which is, now we just calculate, right? 25 plus 36 minus 60 cosine of 37 degrees, which is going to be 61 minus 60 cosine of 37 degrees. All right. All right, so C is equal to plus or minus square root 61 minus 60 cosine 37 degrees. But because we're talking actual physical triangles, you obviously can't have a triangle with a negative length, so we toss the negative sign. All right. Okay, and so, plug this into a calculator, and then you've got C, right? And you can literally see everything on this side, on the right-hand side, is a number. So calculator will just give you a number. And then now you have, once you've done that, right, you have A, you have B, and then you have C. And then you're in the SSS situation. And then you just do the problem as above, right? Using the law of cosines again. So this is the process. I'm not going to actually do it because we actually just saw the SSS. But again, the point here, very, very straightforward. There's no ambiguities or anything like that to have to worry about. Okay, finally, let me just say one word about SSA, right? Which again was the same as ASS, right? This one we dealt with using the law of sines, but it had two solutions and it was kind of a pain, right? We had to recognize that sine might have two solutions, right, between 0 and 180 degrees. And if we just, blindly plugging into a calculator, we might forget that, and then we might very well miss one of the triangles that that exist, right, given those bits of information. Let's try to do this one in the context of, or using the law of cosines and see what happens, right? I think it's going to be a nice computation to do because we'll be able to see why there could be two solutions from a different point of view, right? So again, in the law of sines, there were two solutions because sine of any, if you're solving for sine of something equals a number, there's possibly two solutions between 0 and 180. Here, we're going to see a different reason, all right? So let's say we have A equals, let's do this with numbers. A equals 5, B equals 7, alpha equals 20 degrees. All right. So alpha, beta, gamma, A, B, C, right? We know this is, again, we know this guy, we know B, and we know alpha, right? So ASS, all right? Okay, the point is two consecutive sides and an angle. I mean, you could read it A, B, alpha as well. That would be SSA. All right, in any case, let me use the law of cosines. And the idea here, my thought here, is that I know A and I know alpha. So if I use the law of cosines based on A, then that cosine alpha is going to be known. I don't have to worry about it, right? So let's do that. A squared equals B squared plus C squared minus 2BC cosine of alpha. All right. So I know A, I know B, I know alpha, and I know B here. So I know everything except C, right? Now, there's a C squared and a C. It's not as nice, but I do know everything except C, right? So that makes me feel that I can solve this. Well, that actually does make me able to solve this, right? Just substituting my numbers in just to see this, 5 squared equals 7 squared plus C squared minus 2 times 7 times C times cosine of 20 degrees. All right. Let me clean this up a little bit. This is the same as 25 equals 49 plus C squared minus 14 cosine of 20 degrees C, right? And again, the emphasis here is there's only the unknown C. There's no other unknowns in this problem. All right, here's what's important. That's a C squared, right? That's a c. And so what we have is a quadratic equation. C squared, c, that's a constant, that's a constant, that's a constant. How do we solve a quadratic equation? We throw everything to one side, right? So we end up with c squared minus 14 cosine 20 degrees c, right? Let me put parentheses around this one here. And then I throw the 25 to the other side, so that's going to be plus 24. All right. Equals 0, sorry, equals 0. So here, now we can literally see quadratic equation. C squared, C, constant term, right? This guy here is a number, that guy here is a number. So I can literally immediately write down the answer. C equals minus this guy here, right? Minus of minus 14, so actually that's a plus. 14 cosine 20 degrees, plus or minus root b squared, so 14 cosine 20 degrees, squared minus 4 times a, which is 1, times c, which is 24, over 2a, over 2. Okay. All right, so what do we see? We see that there's two possibilities for c, right? So c equals this plus that, and c equals this minus that, right? And so, again, we get the situation where there's potentially two triangles, right? So this is the same phenomenon as we saw in when we did it with the law of sines, but kind of expressed, the phenomenon is expressed differently in terms of the quadratic equation, as opposed to in terms of the fact that the structure of the picture for sine looks like that. Okay. How could it happen that there's only one solution? Well, if the stuff inside the square root were 0, then it would be this guy plus 0, this guy minus 0, right, over 2, which would be the same solution. So that would be where you only have one solution. When could you have no solutions? Well, if the stuff inside the square root happens to be negative, then there's no solutions. So with this, we can immediately see that there could be one solution, no solutions, or two solutions, right? And again, here it's expressed in the fact that the quadratic equation possibly has one solution, no solutions, or two solutions. All right. So it's really nice, I think, to see that, of course, no matter what method you use to solve these problems, you'll have, the same kind of solutions, but it's good to see that these kinds of phenomenon of multiple solutions can be expressed in different ways depending on how you do the problem. All right. So that's it for the law of cosines. Relatively straightforward. We obviously aren't spending as much time on it because it is a little bit more straightforward than the law of sines. But we will be revisiting the law of cosines very, very, very importantly when we talk about vectors, which is coming up very soon. And it's going to be a really, really important part of vectors. And also, ultimately, that will lead to remember our property cosine x plus y is cosine x cosine y minus sine x sine y. And that was one that we never showed you why it was true. Ultimately, we can explain it using the law, using vectors, which uses the law of cosines. All right. So, even though it seems like, these problems here, we're solving triangles, and you might think, who cares about solving triangles, right? Why would anyone in real life care about solving triangles? Well, first of all, sometimes you do, right? You do need to solve triangles, especially if you're maybe doing engineering, and you are working with kind of triangular structures, maybe, triangular structures of steel, right? Let's say you're building a bridge like this, right? You've got a triangular structure like that to hold the bridge up. A lot of situations where you might want to work with triangles. So solving triangles is something that you might want to do. But for our class, mostly solving triangles is just a an idea that helps us see how law of sines and law of cosines can be used. All right. But remember that actually the most important use of the law of cosines is probably going to be in terms of vectors that we will be talking about soon.